Thanks for starting up and running with Blender. Before we get started, just a quick note about these videos. Personally, I hate watching tutorials that are slow and long-winded. Pausing or rewinding a bit to digest what you just heard means you're engaged in learning. Fast-forwarding because you're bored means you're not. This series has been painstakingly edited for efficiency. They're fast-paced by design so I can cover a complete concept in as little time as possible. Learning Blender will be a lot more fun and intuitive if you understand the basics of how 3D animation works. In this video, I'll explain step by step how computers generate 3D images and the tools and techniques humans use to create 3D art. Don't worry about absorbing all of it in one go. It's meant to be a broad overview, and you'll hear all these terms again many times throughout the series. But also, don't be afraid to pause or rewind a few seconds if necessary. Let's get started. Picture a graph with an x and y axis. A vertex is a point with x and y coordinates that determine its location. Two vertices connected by a line create an edge. A closed shape made of three or more vertices is called a polygon. The surface of a polygon is called a face. Right now, our graph is flat. By adding a z-axis perpendicular to it, we create a three-dimensional space with a center point at coordinates 0, 0, 0. In Blender, this is called world space, and the center point is the world origin. A 3D shape made of polygons is called a mesh. Textures, materials, and lighting can be applied to the faces of a mesh, and that's what you see in a rendered image. Meshes can get pretty complex with thousands or even millions of vertices. It wouldn't make sense to try to manage all these coordinates individually, so that's why meshes, and everything else, exist inside containers called objects, which are really just additional 3D graphs with their own local space. Now we can move, rotate, and scale the object in world space, and any meshes it contains will keep their shape relative to the object origin. Say we have two objects. If we parent object B to object A, object B will behave the same way, rotating and scaling around object A's origin point. However, we can still move and rotate object B independently, and its meshes will follow their own origin point. This is the basic concept that makes 3D animation possible. Every Pixar movie, every Marvel villain, every CG starship or dragon you've ever seen were really just complex hierarchies of points on graphs inside of other graphs. Basic changes like moving, rotating, and scaling objects are called transformation. More complex changes like character animation, where a mesh actually changes shape, are called deformation. But to animate something like a person walking, the vertices still need something to rotate around. This is where armatures come in. An armature is an object that contains a hierarchy of bones, each with its own x, y, and z axes. The bones are defined in the armature object's local space. They are animated, however, in what's called pose space. Animation is created by placing the armature into the desired pose at a specified frame on a timeline, and creating a keyframe to save the location, rotation, and scale values of each bone at that frame. The computer will automatically fill in the poses between keyframes, and this creates the illusion of movement. To deform a mesh with an armature in Blender, we create vertex groups corresponding to each bone. Each vertex can belong to multiple groups where it gets assigned a weight value that determines how much influence that bone has on it. When the animation is played, the character and armature objects don't move. Instead, the armature moves in pose space, and the mesh is carried along with it based on its weights. To apply textures to a mesh, we use a UV map, which is a 2D representation of the mesh broken into user-defined segments. Imagine cutting a shirt along the seams and laying each half out flat. This is the basic idea of UV unwrapping a mesh. Now we can paint a texture, and the UV map wraps it around the mesh's surface. Before we can render our animation, we need to be able to see it, so we add lights and a camera. These are just different types of objects, but with a lot more traits we can animate, like the strength, fall-off, and color of lights, or the zoom and focus of the camera. When we start rendering, millions of virtual light rays shoot outward from the camera in every direction it can see. They bounce off any objects they hit and continue bouncing around the scene until they hit a light. It's more efficient to only calculate the light rays that hit the camera, and it's easier to do this by tracing their path backward to the light source. This process is called ray tracing. It can result in photorealistic images, but takes a very long time to render even a single frame. Rasterization is a different rendering technique mostly used in video games where the computer needs to render many frames every second. Rather than simulating millions of light rays every frame, it estimates the color and brightness of each pixel based on the texture of the object in that pixel and how far it is from the light sources in the scene. This technique is less accurate but much faster. Now that you understand all that, learning how to work with Blender should make a lot more sense. Let's get started.